In this video, we would be learning how to assemble the global stiffness matrix and stiffness equations using the direct stiffness method. Assembling the stiffness matrix by superposition or by the direct stiffness method is a reliable method of directly assembling the individual element stiffness matrices to form the total structure stiffness matrix and the total set of stiffness equations. Individual element stiffness matrices are simply superimposed to obtain the global stiffness matrix. In order to superimpose the element matrices, they must be expanded to the order or size of the total structure stiffness matrix, and they must be also expressed in global coordinates of the system, as we're going to be seeing in following chapters. In order to demonstrate this message, I'll be referring to the example that we completed in the previous section. So we'll be looking at the assemblage of two springs, K1 and K2. So I'm looking here at a structure that may be discretized by element 1 and element 2. Element 1 extends between node 1 and node 2, and element 2 extends between node 2 and node 3. The assemblage has a global coordinate axis x, and this assemblage is subject to external forces F3 x, and at node 2 we have F2x, and of course at the support we have an unknown support reaction that I'm gonna call here F1x. And please note, for all the external forces, I'm using an uppercase F. Having discretized this system, I can look at the individual elements. But before we do that, let me also identify the degrees of freedom of the entire system. So at each node, since these are springs aligned in the x-axis, along the x-axis, and only subject to forces along the x-axis, we're going to have 1 degree of freedom per node. So at node 1, I'm going to have degree of freedom U1. At node 2, I'm going to have the degree of freedom U2, and at node 3, I'm going to have a degree of freedom U3. So we can see here that for the entire system, we have 3 degrees of freedom. And this is important because, as we're going to see, the global stiffness matrix is going to be of an order 3 by 3 based on this 3 degrees of freedom. Next, we're going to look at each element separately. So I'm looking here at element 1, extends between node 1 and node 2, and it has a stiffness K1. Now, this may be aligned along the local axis x1. And please note that in this case, the local axis is same as coordinates, which makes things simpler because the local stiffness matrix is going to be the same as the global stiffness matrix for these elements. This is also true for element 2 that extends between node 2 and node 3 and has a stiffness K2. It has a local axis x2 that is aligned along the same direction as the global axis x. For each of these elements, I can identify the nodal forces. So for element 1, I'm going to have at node 1, F1, comma 1, identifying that this is applied to node 1, element 1, I'm sorry. And at node 2, I'm going to have an F2, comma 1. Likewise, for element 2, I'm going to have an F22, and at node 3, I'm going to have an F3, element 2. We can also identify the element degrees of freedom. So I have here U1 for element 1, and I have here U2 for element 2. Element 1, I'm sorry. For element 2, I have a U2 element 2 and a U3 element 2. Next, as we have already done in the previous section, I'm going to rewrite the element stiffness matrices for element 1 and for element 2. And as we have learned, the stiffness matrix for a spring element may be expressed by K1 minus K1 minus K1, K1. Likewise, here I'm going to have a K2, a minus K2, minus K2, and K2. In order to superimpose the element matrices, we must first expand them to order size of the total structure stiffness matrix uppercase K, or the total structure number of degrees of freedom, which is in this case is 3 degrees of freedom. We simply add rows and columns of zeros for displacement that are not associated with that particular element. So let's see exactly how we're going to do it here. If you look at element 1, we have degrees of freedom is associated with the degrees of freedom U1 and U2. So U3 is not existing in the stiffness matrix of element 1. This is also true for the columns. I have here U1 and U2. For element 2, I have here 2 degrees of freedom, U2 and U3, U2 and U3. So it is missing here U1. So how are we going to do that? I'm going to rewrite the element stiffness matrices K1 and K2 and instead of writing them as a 2 by 2, we're going to write them as a 3 by 3. So instead of this 2 by 2, this is going to become a 3 by 3. So I'm going to go here and put my brackets. I'm going to come here and put my brackets. So these can go nicely into the global stiffness matrix. Before I start writing, I would like to label my degrees of freedom. So I'm going to go for the global degrees of freedom, or this total of 3. And I'm going to go like U1, U2, U3, U1, U2, and U3. Same here, U1, U2, U3, U1, U2, and U3. I'm going to take the elements that belong to these degrees of freedom and just put zeros for the ones that do not exist. So for K1, I'm going to have here a K1, a minus K1, a minus K1, and a K1. And then we're going to add the zeros. So I'm going to have a 0, a 0, a 0, a 0, and a 0. Likewise, I'm going to do for K2, Now for K2, if you look at my matrix elements, I have in row 2, column 2, I have a K2 corresponding to U2, U2, corresponding to U2, U3, I have a minus K2, and corresponding to U3, U2, we have a minus K2, corresponding to U3, U3, I have a plus K2. For the non-existing elements, we are simply going to fill in with zeros in the rows and the columns. So these are the expanded element stiffness matrices that we can use directly to superimpose them together or add them together to form or assemble the global or the total structure stiffness matrix. As you recall from the previous section, that the element stiffness matrix may be expressed as F equal to K times U. If I apply this for element 1, we had F1, 1 and F2, 1. We said this was equal to K1 minus K1, minus K1 minus K1 and a K1 was equal to U1, U2. Now, in order to use the expanded element stiffness matrix, I'm also going to do the same with my element stiffness equations. So I'm going to go for element 1, I'm going to have an added 0, so F1, 1, F2, 1, and then on the third row, I'm simply going to add a 0, and this is equal to, I'm going to use my expanded stiffness matrix. So I have here K1 minus K1 minus K1, K1, and I'm going to complete here the zeros. Multiply by U1, U2, and strictly speaking, this is U1 element 1. That is, as we have said from compatibility, is going to be the same as the global structure. And then we are adding here a U3. Okay. We can do the same for element 2. I'm going to skip the first step here, so I'm going to go directly to write the element stiffness equations. For node 1 is non-existent, so we're going to have a 0. Then I'm going to have F2, 2, and F3, 2. Okay, let me write them in blue to be consistent. So I'm going to have here F2, 2, F3, 2. This is equal to, and I'm going to go put my zeros in the first row and the first column, and then I'm going to put my stiffness elements, K2 minus K2 minus K2 and K2. Multiply by U1, U2, 2, and U3, 2. Now, from equilibrium, we were able to say that F1 from equilibrium of the nodes we were able to say that F1x is equal to F11, F2x is equal to F11 plus this is F21 plus F22, and F3x is equal to F32. And we can write this in matrix form as F1x, F2x, F3x is equal to F lowercase f11, f21, and 0, which is the nodal element forces for element 1, plus f2, sorry, there is a 0 here, the first entry is a 0, and then we have F22 and here F32. So simply said, the external forces can be written as the sum of the element nodal forces as expressed in the element stiffness equations here. From compatibility, we also were able to say that U1 for the global structure must be the same as U1 element 1, and even though element 2 does not exist, but would be the same as U1 2. So I can really, even if I put here a 2 which is not existent and I put here a 1 which is non-existent, but compatibility and make sure the structure remains continuous after displacements, U2, where the two elements connect, has to be the same for element 1 and also for element 2. This is also true for U3, must be the same for element 1 and element 2, even though element 1 is not connected to node 3. Next, we can write the global structure equations based on this equilibrium equations. So we can say that this F1x, F2x, and F3x is equal to K1, the expanded, the 3 by 3, multiplied by the global degrees of freedom, U1, U2, and U3, plus the expanded K2, which is the 3 by 3, multiplied by U1, U2, and U3. Or I can say that F1x, F2x, F3x is equal to, I take the displacements as a common factor here, and then put the sum of the two expanded element stiffness matrices. And this is how we superimpose them to find the global stiffness matrix that is a 3 by 3. So based on that, I can say that this here is the global stiffness matrix K. And this global stiffness matrix K may be written as K1 minus K1, and then we are going to get a 0, and then we have a minus K1, a plus K1 here, and then I'm going to get entries from my second element stiffness matrix. So I'm going to have here a plus K2, a minus K2, a minus K2, and a plus K2. And of course here we are going to still have a 0. And this is my global or my total stiffness matrix K, that is a 3 by 3. So my total or global stiffness equations may be then written as F1x, F2x, F3x equals to K1 minus K1 0 minus K1, K1 plus K2 minus K2 0 minus K2 and a plus K2. The expanded element stiffness matrices, typically in the global coordinates, in this example it didn't matter because the local coordinates or the element coordinates were the same as the global coordinates, could then be simply added directly to obtain the total stiffness matrix K. This is a reliable method that is called the direct stiffness method. And I'm going to demonstrate here quickly how we can do that. So if we look at the element stiffness matrices, K1, the 2 by 2, we had a K1, a minus K1, a minus K1, and a K1. And please note that the corresponding degrees of freedom here were U1, U2, U1, and U2. Oops. For the second element stiffness matrix, K2, the 2 by 2, was equal to, we had this K2 minus K2 minus K2 and a K2. And I'm going to show the corresponding degrees of freedom, U2, U3, U2, and U3. For a problem with large numbers of displacement, we can avoid the expansion of each element stiffness matrix by labeling the rows and columns of each element stiffness matrix, as I just did, according to the degree of freedom associated with them. Then we can construct the global or the total stiffness matrix K directly by adding terms associated with degrees of freedom into corresponding identical degree of freedom location in the global matrix K. So let me show you exactly how we're going to do here. I'm going to form the global stiffness matrix K, which I know is a 3 by 3. And I'm going to say this is equal to, and I'm going to open my brackets, and I know I'm going to have 3 rows and 3 columns corresponding to the degrees of freedom. So I'm preparing here for my matrix, and I'm going to label my degrees of freedom corresponding to column 1, column 2, and column 3, column 1, I'm sorry, row 1, row 2, and row 3. For row 1, column 1, I see a contribution only coming from element 1, and this is going to be K1. For row 1, again, there is no U1 for element 2. So everything is coming here from element 1. I'm going to get here a minus K1. Then row 1, column 3, we do not have any contribution from any of the elements, so we're going to get a 0. When I go to U2, I have a column U2 for both elements 1 and 2. So we're getting contribution from both elements. So this is where we are going to superimpose or add the terms directly. Column 1, I have a minus K1. For column 2, I have a K1, and then I have a plus K2 that is coming from here. For row 2, column 3, we're going to have this minus K2. And if I continue here, I got a minus K2 here and a plus K2. And then we're going to fill in a 0 here because we don't have any contribution. So as you can see here, element 1 contributed the blue entries into the global stiffness matrix, and element 2 contributed the red entries into the global stiffness matrix. And of course, the zeros is where we do not get any contribution from any of these elements. This is the direct stiffness method where the expansion of the element stiffness matrices may be avoided, and we come to the same conclusion simply by making sure that we label the rows and columns for each of the element stiffness matrices, and then we construct the global stiffness matrix directly by adding terms associated with each degree of freedom into the corresponding identical degree of freedom location in the global matrix K. This concludes the direct stiffness method video, and we will be looking next at a complete solution.